Okay, so now I think I basically introduced the first type of moment, which is called a moment of a force about a given point. Now I want to show you two examples, okay, how to calculate the moment of a force about a point. So let's talk about the first one. The first one, obviously, two-dimensional problem, because when you look at the picture, that's two-dimensional. And after I'm done, I'm going to show you another one, which is three-dimensional problem. Okay, let's do one by one. I'm not sure whether I can finish all these two examples, but let's do one by one, right? Let's look at the first one. This is the first example. Let's say we have 100 pounds vertical force acting on point A. Okay, 100-pound vertical force is applied to the end of lever here, which is attached to a shaft at point O. Okay, so these are the basic geometries given. There's a force acting on point A, and then there's the point O. And the geometry from A to O is given 24 inch, and the angle between this and the horizontal line is 60 degrees. So these are all the basic geometries we know. So we need to calculate A, B, C, D, E. Let's first talk about question A. The question A asks us to calculate the moment of this force about a point O. Oh, that's exactly the definition or the introduction of the first kind of moment, right? So what is the moment of this 100 force about point O? So first of all, we know this is a two-dimensional problem. So if we are dealing with a two-dimensional problem, basically we can use R cross F, or we can use what we call clockwise, counterclockwise. So it's really up to us. We have two tools to deal with two-dimensional problem. So now, let me say I'm going to use what we call the F times D equation. The only problem is, can we find the short distance? Well, let's give it a try, right? The moment, the magnitude of the moment of this force at point O is F times D. What is the F? The magnitude of this force. This force going down, but we know the magnitude is given, 100 pounds. So the magnitude of the force is 100 pounds. So that's F times D. D is a short distance. So now let's go back to look at the short distance. By definition, the short distance is from the point you want to calculate the moment, that's point O, to the force line. Okay, so this is the force line, vertical direction, that's a force line. So this is a force line. What's the short distance? This is a short distance. Okay, so from this triangle, you have 24 and then times cosine of 60 degrees, which is sine 30. That's half, so that's 12. Well, that's extremely easy for us to figure out the magnitude of the moment, which is 100 pounds times 0.5. Okay, let me show you now. The first question, right? To calculate the moment of this force about this point O. Okay, so we're going to use F times D equation because we can figure out D. If not, then we have to go back to the original method, right? Okay, so back to this again. What's the magnitude of F? 100 pounds. Why did not? Oh, here, 100 pounds, right? And what's the D? D is a short distance, again, from the point you want to calculate the moment to the force line. So this is a force line, and obviously this is a short distance called D. So from this triangle, D equal to 24 times cosine 60 degrees. Cosine 60 equal to 30. That's why 24 times half, that's 12. So finally we end up with the magnitude of this moment, which is equal to the magnitude of the force, 100 pounds, times the short distance with a 12 inch. Then that's easy, right? That's a 1200 pounds inch. And finally, never forget about this unit. So pound times inch, because this is a pound and this is inch. Okay, so this is the magnitude. But you need to also identify the direction, even for two-dimensional problem, because anytime when we talk moment, we have direction. So what's the direction? If you're using F times D, you need to say either it's a clockwise or counterclockwise. So now we have this force going down. You have this vector D. So obviously, this force has the potential to rotate this rigid body at point O in a clockwise way. So if it's a clockwise, finally you put a negative sign in the front. So finally, you gave this moment. This is a moment, which is a vector, indicating the direction, which is a counterclockwise, and also the magnitude. So you can either just finalize with this. You can also say or the magnitude, and you use this kind of symbol to indicate it is clockwise. So it's up to you. But you need to say either this or this. You can choose whatever you like. The bottom line is you need to give the magnitude. You also need to give the direction. Any questions? That should be extremely simple, right? Okay, because this is the typical first kind of moment of a force about a given point. Okay, now let's go back to look at the second question. Second question, we need to determine the horizontal force at this point O. This time, you see, that's the first time we mentioned a horizontal force, right? A horizontal force at point A, which creates the same moment. So this time, instead of looking at a vertical force, let's forget about the vertical force, for example, right? The new question saying there is a horizontal force at point A this time, but this horizontal force will create the same moment. Back to question A. From the question A, we already got the moment. So now the question is, instead of having a vertical force, can we have a horizontal force? The moment of this horizontal force about point A, about point O, is the same with this. Okay, so that's the second question. Okay, fine. So let's say we have a horizontal force. Okay, so this is a horizontal. You may say, well, why now to go to the lab? Well, nobody knows until we finally figure out. Okay, it doesn't really matter. If you really do not know it, you just assume to the right or you assume to the left. It doesn't matter. We'll figure out. Okay, obviously for this problem, it's going to be to the right because the same moment means not only the magnitude but also the direction must be the same, which I'm going to briefly explain to you. Let's say we have a horizontal force acting on point A. And unfortunately, this time, we do not know the magnitude of that force. Okay, we do not know the magnitude of the force. However, this force will create the same moment at the point O compared with the previous one. Let's say we have a force acting on point A horizontally. Then the question is, what is the moment of this force about point O? Same thing, what we call F times D, right? So the moment of this force about point O is equal to the magnitude of this force. You do not know it, you call F. Use a symbol. Multiply the shorter distance. What is a shorter distance? Well, we need to figure out the shorter distance. The shorter distance, by definition, is the distance from the point you are calculating the moment on to the force line. But this time, the force line is this. This time, the force line is horizontal. So if it's horizontal, then what's the shorter distance? This is going to be the shorter distance, right? This is going to be the shorter distance, which is called D, with the right angle here. So then this shorter distance should be 24 times sine of this angle, 60. This is 60, this is 60, right? Or is it this is the short distance? So 12, where's the 12? Oh, they already gave you it directly. Oh, here. Okay, so this is D. Okay, so 24 times sine 60. When you punch your calculator, you find out that's a 20.8 inch. It's a short distance. So then the moment of this force about this point is equal to F times 20.8. And from the statement, it says this moment should be identical with this. And this one, we know it. We know it. The magnitude is 1200. So then we just put the 1200 on the left-hand side. This is the one we got from the previous question A. This is equal to the moment of this horizontal force. So from this equation, you can figure out the magnitude of this force. Okay? Which is finally end up with 57.7 pounds. Okay? So this is what we call the magnitude. But we also need to identify the direction. There's only two possibilities in terms of direction because they already told you it's going to be horizontal direction. So either this or this. Obviously, if you have a force horizontally to the right, then the moment of this force about point O is clockwise. And in fact, to be identical with the previous moment, you also need to have clockwise. So that's why, in fact, it is horizontally but to the right. If you say, no, I'm going to talk about something horizontally to the left, then this force will create a moment in a counterclockwise direction at point O. Then actually it's not identical. Okay? So to complete the question B, the horizontal force at the point O, or at point A, which create the same moment, is a force at point A to the right horizontally with a magnitude equal to 57.7 pounds. Any questions? Okay, so then we complete the second part, right? The question B. So basically they ask you, why must the direction of this force be to the right? Of course, because it's clockwise we need to generate. Okay? Okay, so assuming we are pretty comfortable dealing with question A and B, now let's move to the next one. Question C. The question C is something different from the previous two, okay? So this time, instead of having a vertical force or instead of having a horizontal force like A and B, this time they say, okay, now we don't know the direction of the force, okay? But there is a force acting on point A. There is a force acting on point A, but it's not vertical, it may not be horizontal either. So they say we need to determine the smallest force at point A which produces the same moment this time. Okay? So this force for question C is not horizontal, may not be vertical, but it's the smallest force. However, such force will create the same moment with question A or question B. In other words, with the smallest force acting on point A in a certain direction, it's going to create a clockwise 1,200 pound-inch moment. And it's our job to identify that smallest force, including the magnitude, including the direction. Okay? Let's talk about question C. Well, if you look at the question C, you can just arbitrarily give directions of force at point A. It can be any direction, right? So let's say we have this direction with a certain force. We're going to calculate the moment at point O, which is equal to 1,200. Or this one, create a moment, this one, this one, this one, this one, any one. However, among all these possibilities, the correct answer should be one of these with the smallest magnitude. Okay, so the bottom line is you are going to use F times D concept to calculate the moment, but the moment with the magnitude is fixed with the 1,200 as we calculated before. So if F times D equal to a constant, now you can freely change F, and of course you can change D. Then what is the scenario? One symbol multiply another one, but the product is constant. So if this F should be the smallest, then this D should be the largest. Okay? In order to maintain the result as a constant. So you have two variables to change, F times D. Okay? So if this goes larger, then go smaller. If this goes smaller, this goes larger. Now, from the previous description, they say F has to be the smallest one. If F has to be the smallest one, then D must be the largest one. So going back to look at these two scenarios, one is this D, right? You can calculate, which is this one, 24 times the certain angle, and you look at the other one, which is also 24 times certain angle. You can change this angle because that changes the direction of the force. So in order for it to reach the largest D, then that angle should be 0. In other words, the smallest distance D in general, the largest D in general is D times sine or cosine with angle. And then you want to reach the largest one, then that's equal to D times sine 90 degree or D times cosine 0 degree. So in other words, this is D, which is 24. Okay? You cannot find D greater than 24. So 24 is the largest D. And if that's the case, going back to look at this equation, the left-hand side is assigned to be 1,200 from the previous two cases, which is equal to F times D. You try your best to minimize F, but then at the same time, you need to maximize D. The maximum value of D should be 24 inch. So then 1,200 pounds equal to F times 24 inch, then you can easily get F from this equation, which is 50 pounds. So now you find out the magnitude of the smallest force acting on point A, which is 50 pounds. Also, you need to give the direction of this force, because the problem doesn't tell you the direction either. So you need to identify the magnitude. You also need to identify the direction. Now you figure out the surety distance is 24 itself. Then what? Then the force must be perpendicular to this shaft. This. Let me see a picture. Oh, we don't have a picture. Okay, basically you need to give this direction. Okay, so this direction is perpendicular to this. And that's serve the direction of the smallest force. And also somehow going to that direction so that overall rotation is clockwise as well. And that's the third question, okay? Going back to here, the third question, calculate the smallest force at point A, which produce the same moment, which is 50 pounds. Finally, two more. What is we need to determine this time, okay, the force may not be acting on point A. All the previous three questions are talking about a certain force at point A, just different directions. Now this time, question D, we need to determine the location of a 240 pounds vertical force acting on somewhere, now we don't know, which can produce the same moment. So this time, if you look at this force, number one, the direction is given, is vertical. Number two, the magnitude is given with a 240. However, we don't know where the force is applied on. And we need to determine where, the location. We need to find out the location of this force which produce the same moment. Now that's the question D. Okay? We don't know it. We just randomly pick somewhere. Let's say we have a force, vertical force, with a magnitude 240, vertical. There's a vertical force, right? At point B. Unfortunately, we don't know the location. And it's our job to locate the location. Okay? Same thing. We use this F times D concept. The left-hand side is equal to 1200, as we obtained previously in A or B or C, which is equal to the right-hand side, F times D. What is the magnitude of this F? It's given 240. So we put 240 here. But D is unknown. It's a shorter distance, right? The shorter distance from O to this force line. So this is a force line. This is a force line. This is a shorter distance D. So this is D. However, what is D? This D, of course, is 1200 divided by, this D, 1200 divided by 240, right? You got D, with 5 inch. So, you try to find out the location of point B. In other words, you need to calculate OB. What's the distance from O to B to locate where the force is applied. So then let's say OB times cosine of this 60 degree, that should be equal to D. So D, which is a 5 inch, which is equal to OB times cosine 60. Then, of course, you finally find out OB, the distance from O to B, is 10 inch. And that basically gave us the answer about the location of that vertical force. So in fact, there must be a force located at point B with a distance from O to B as 10 inch. Okay? So that is the question number D. Go back to here. So the location, that is 10 inch from here to here. Okay, so the last question is concept question. Whether any of the forces from question B, question C, or question D is equivalent to the original force. The answer is no. They are equivalent, but in terms of forces, they are all different because those forces are acting on different locations. They are equivalent, but they are not the same thing. In other words, when you have a force at the point A going down versus a force at the point A going to horizontally, these two are giving the different scenarios. However, these two forces just happen to produce the same amount of moment at point O. But these forces are fundamentally different from each other. And that's what I call the concept question. Even though you can calculate the equivalent one, but it doesn't mean forces themselves are the same thing. Because when you look at the magnitude, they're all different. When you look at directions, they're all different. Any questions? So this is a typical two-dimensional problem just to show you how we can use F times D equation to identify the moment in two-dimensional setting. First of all, you need to use F times D to find out the magnitude, and then you need to use a clockwise or counterclockwise to determine the direction. So that's a two-dimensional problem. Okay? Now, let's move to another problem, which is a three-dimensional problem. Three-dimensional problem, we have a rectangular plate here. Rectangular plate is supported by the brackets at point A and point B. These are supports. In addition, we have a cable from C to D. Just a cable, right? CD, a wire. Knowing that the tension or the magnitude of the cable force is equal to 200 Newton. Okay, so we know the magnitude of the cable force is equal to 200 Newton. Now we need to calculate the moment of this force exerted by the wire at point C at point A. So in other words, we need to find out where's point A. This is point A, right? So what is the moment of this force? What is the moment of this force about point A? And that's a question. Okay, that's a typical three-dimensional problem this time. So how to solve it? Well, for any three-dimensional problem, just do not think about so-called F times D. In general, it doesn't work because it is very difficult to find out the short distance. You may say, well, from this picture, the short distance from A to this force line. This is a force line, right? It's going to be from here to here. Well, unless your geometry is so good, I don't know how to calculate this one because it's three-dimensional setting. It's not that easy, in fact. Okay, so then just forget about it. On the other hand, it's very simple if you use this equation, in fact. And this is the definition of the three-dimensional moment. Okay, so how to calculate the moment of this force at point A? Well, identify two vectors and conduct a cross product. That's it. The first is the vector distance vector. That means from A to C. From A to C. Whether you want to write this one C/A, which I really do not know, but normally what I try to memorize is from A to C. A is the point you try to calculate moment on, and then C is the point the force applied on. So that's why from A to C. In other words, C subtract A. And that's the first vector. And the cross with the force vector. Of course, we need to identify the force vector as well. Okay? So that is kind of the concept. Now, let's go back to deal with this problem in a mathematical way. So I'm going to basically plotting the same thing with a thin plate. And there's a force acting on point C going up. By the way, you need to figure out this force is from C to this direction, not going downwards. The reason is because of cable. Again, cable can only provide tensile force. So that's why this cable provides the force at point C going up. And that's called the force. R is from A to C. So R cross F. You need to figure out R, A to C. That means you basically use a C subtract A. You find the three component of point C, subtract three component of point A, then you can find this R. So you need to set up the Cartesian coordinate system first. At the very beginning, we may not give you, but then it's up to you to set up a Cartesian coordinate system. Let's say we choose this at original point O, and this is the x direction, this is the y direction, this is z direction, mutually perpendicular from each other. And then we can find out the three components of this point C. At this point C, the x component is 0.3, y component is 0, z component is this one. You add them together, and that's the z component. Three component point A, x component 0, y component 0, z component is this one plus this. Then you can finally end up with the R, which is called distance vector. After you get this one, then you need to separately, let's call this the step number 1. Step number 2, you need to calculate the force. Force, which is the vector, is always equal to the magnitude of the force multiplied the unit vector. So we need to recall what we did in chapter 2. So this is always the equation to calculate the force vector. The magnitude, we're given with a magnitude 200 Newton, multiplied unit vector. What's the unit vector in chapter 2? All we need to do is to find out 2 points in the previous chapter. If you just happen to forget, go back to look at chapter 2. Find 2 points. This is the fourth line. Obviously, we have 2 points, which is called the point C, which is called point D. So we use a D subtract C and divided by the distance, you can get this lambda, which is a unit vector in the fourth direction. And then you simplify the mass, this is what you have. So finally you get the 3 components of the forces, you put in here, you find the 3 components of the distance vector, put in here, and the first row is always ijk, and you need to calculate the determinant, which is finally end up with this. If you don't know how to calculate the determinant, again, you use a cross product by yourself. You should finally end up with this one. Again, you need to finally write the unit. Don't forget with the right unit. So this first assignment due this Friday, almost all problems need to come with a unit. And don't forget that, okay? So I'm going to stop here, and then next time I'll continue with the second type of moment.